Okay, let's just find a little bit of information off of a graph. So finding g of 0 graphically. So this is the g function. X is our x value is 0. So if you think x is 0, seems to hit right about here. So g of 0 is somewhere around negative 1.5. Let's look at a few other values. So what is g of 2, for example? So if you look at the graph, this is the g function. We're plugging in an x value of 2. And so when x is 2, the y value, or the g of x value, the g of 2 value would be about 1.5, positive there. Let's try g of negative 1, just so you get the idea. G of negative 1, x is negative 1 right here. It hits the function right here. It's the point negative 1, comma negative 2. So negative 2 is that value. Dealing with just variables here, what is h of a? So right? The h function is this. A is here. So just like we looked up an x value that were numeric there, if we look up at a value like a, we find that point somewhere around here. That distance, how tall that is going to be our h of a value there. And so, to find h of a, you plug in. So that point right there is really the point a, comma, h of a. H of a is the vertical distance. It's the y value of that point. So think of that as a vertical distance. Whatever that vertical distance is h of a. Just like here, whatever this vertical distance was, although it's in the negative here, but it's the distance of negative 2 there, a distance of 2 in the negative direction. So applying that, the definition of the rate of change, if y equals f of x, then the average rate of change, that's a key word here, the average rate of change, which we used to call the slope. We kind of think of it like an average slope with respect of y with respect to x on the interval a, b is this. So let's derive this formula. So instead of just kind of like, this is the formula we're using today. It used to be called the slope formula. Remember, like changing y over changing x. So that's our new slope formula, and here's why we can do that. So kind of like we did in the last example, we have a for our x value here and b. I want to find the slope from this point to that point. The one thing I do know in the ordered pairs, that's a. I don't know the y value yet. The x value of that point is b. Right? We know that from the x value being a and the x value being b here. And so if you think about function notation, remember we used to call this kind of point, like any point on a function, we used to call it x comma y. And remember the days when we go, oh no, that's no longer y, that's really like your f of x value. So if you think about it that way, x comma f of x, this is a, what's the y value? Well, kind of like we just did, it's going to be f of a. If this is b, what's the y value? Well, if the x comma f of x, this is just going to be, this is the f function, this will be f of b. So using those y values, you can see where the slope formula comes from. In other words, do you remember y2 minus y1 over x2 minus x sub 1? So think about it. Y2 minus y sub 1, f of b minus f of a. B minus a, or your x values. It's really the slope formula in disguise. So we're just kind of repackaging slope. I really rather you think of slope as the average rate of change. Notice there's a lot of different slopes here. Like if you looked at the individual slope, like right here, it looks like a slope. It gets a little shallower right there, so it's almost 0, a slope of 0, very close to there. But we're really looking at an average slope. So you're taking 2 points and just finding the slope between those points. Even though the function may do all kinds of stuff in here, the average slope would be, from this point to this point, just in a straight line. The average rate of change. So you could be increasing, decreasing, but the average would be just the slope between those 2 points. And so that's basically what we're finding here is the slope between 2 points. So let's use this to find this. So find the average rate of change of the function between x equals 2 and x equals 5. So we're going to use the formula f of b minus f of a over b minus a. We're basically given a and b. It doesn't matter which one you choose as what. I'm just going to choose 2 as a and 5 as b. Right, so writing this down and figuring this out, this is our function f. So this would be f of b, which is 5, f of 5, minus f of a, which is 2, over 5 minus 2. That's b minus a. So how do I find f of 5? Well, we got the function there. Can't we just plug in 5 right there? So that'd be 5 squared minus 9. 25 minus 9 is, what, 16? Minus f of c, let's plug that in for x. So that'd be 2 squared. 4 minus 9 is negative 5. All over 3. 16 minus negative 5 is like 16 plus 5. And so we have 21 over 3, which is 7. So the average rate of change of this function is 7. Now, you certainly don't have to graph this at all. I'm just going to kind of roughly sketch this out here so you have a sense of what this might be. So I'm going to get some graph paper here and roughly sketch it out. So this function looks something like this. So if I were to graph x squared minus 9, there's a y-intercept right there. Just a few points. Let's see. 3. See, that's 9 right there. The graphs look something like this, roughly. Real rough graph. I know that's not very good. If I were to try and plot these points, so when x is 2, that looks like x is 2, that would be a y value of negative 5 there. And this is going to be hard to see, but when x is 5, it's going to be way up here. It's going to be right, a point way up here at 5, 16. And so even though it's kind of curved in there, it's a parabola there, it's definitely not straight. If we were to draw a straight line from there to there, that average rate of change is 7. There's a slope of 7 between those 2 points. That's basically what we just found. So I just wanted you to see it a different way graphically, just so you have that perspective. Let's find another one here. So average rate of change from on this function. So it would be f of b, which in this case, let's make this a and this one b. So f of 4 minus f of 1 over 4 minus 1, using our formula. Plug 4 into the function. That would be 2 times 4 is 8, plus 1 is 9. Minus plug 1 into the function, 2 plus 1 is 3. Over 3, which would be 6 divided by 3, which is 2. So the average rate of change of the function is 2, which actually shouldn't surprise you. What's the slope of this function? It's 2. Right? If you think about what the graph of this might look like, it would be 2x plus 1 is right here. Looks like a slope of 2. Really everywhere on this line, the slope is 2, right? So it doesn't matter which interval I pick. In this case, I picked from 1 to 4, right? The slope is 2. If I picked negative 2 to 1, the slope would be 2. The slope of everything on that line, it's linear. So that'd be kind of a silly one. I can almost just go, oh, the slope is 2. Usually we're taking graphs that have some curve to them and finding the average rate of change, but we could do a linear graph and it still works. Let's find another one here. So f of, let's call this, oh, this is kind of weird. Well, I'm going to call this one A because it's already called A. I'm going to call this one B. No, I'm just going to, I hope this won't mess you up. I'm going to keep it the way it is just to show you that I'm going to call my B value. So those are the two values. So I'm going to call my B value, I'll call this my A and this my B. I'm not going to change things. So A and B. So f of B would be f of A minus f of negative 2 over A minus negative 2. So we get f of A. Well, let's see, what is f of A? Let's plug A into the function, right? So f of A is when I plug A into that function for x. And so this would be, f of A would be a squared plus 4 getting complicated. Minus f of negative 2. If I plug negative 2 in there, that would be negative 2 squared, which is 4. 4 plus 4 is 8. And then this would be a plus 2. Well, I'm hoping something simplifies here. Let's see what happens. So we get a squared minus 4, I like that, over a plus 2. That can simplify further, I think. So that would be, I think I can factor the numerator. A plus 2, a minus 2, over a plus 2. Maybe you see the factoring, the canceling I see. A plus 2 over a plus 2 is 1. So this would just be a minus 2 is the average rate of change between those two. So we can even plug in variables there, and it works out just fine. In fact, it worked out really better than I thought it was going to work out there. So that's nice when that happens. So the last example I want to talk about is more real world. The man is running around an oval track that is 200 meters for one lap. The observer uses a stopwatch to record the runner's time at the end of each lap, obtaining the following table. What was the man's average speed between 68 and 152? So 68 and 152 here. So let's just use the formula, right? So let's call this our A and this our B. Let's just use the formula. So this would be f of 152 minus f of, I guess, 68 over 152 minus 68. And so I'm just going to plug this into the f function. Oh, wait a second. We don't know what the f function is. So this is going to be a little tougher. You have to think about it. But think about it. This is like an f of x value. F of x is really what in disguise? When you see f of x, isn't that just a y value in disguise? Right? So f of 152, if I know that my x values are time and my y values are distance, what's f of 152? Well, it's right there staring at me. What's f of 68? It's right there. So I can really plug in those values, because those are my y values that go with those specific x values. Now, there's a lot of fluctuation. There's no real function here, but we're taking average rate of change anyway. It should work out just fine. So f of 152 is 800 minus 400 over, let's see, 152 minus 68, 4, 8, 84. And so this would be, what, 400 over 84, which is 200 over 42, which is 100 over 21. Which it might just be good to think about that in terms of like more of a mixed number. I don't usually do this, but it would make more sense here. So 21 goes into 100 4 times 4, and that would be what, 84. So and 16 21s. So almost 5. What is this asking for here? What was the man's average speed? So this would be meters per second. So meters per second. So this would be 4 meters, almost 5 meters per second. So 4 and 16 21st meters per second. So if we want to think about this in real world stuff, that's what his average rate of change was. Because it looks like he was going at different speeds, right? When he starts out, he's going in 32 seconds he went 200. But the next 32 seconds, that would be 64. Yeah, he got a little slower as he's going. I think that trend continues as he keeps going. He gets a little slower and slower and slower as he keeps running, which is definitely the way I keep running. I get slower and slower and slower. My wife gets faster and faster, but I get slower and slower when I run a further distance. That was the lesson for today.